Okay, so in this video, we're going to be continuing what we started in class. So I want to look at the Rolle's theorem, the mean value theorem, linear approximation, and differentials. All right, so here are just a few additional things that we can look at now that you know how to do a derivative. All right, so with Rolle's theorem, it's really saying something pretty simple. It says if you have a function that is continuous on an interval and differentiable, except maybe at the endpoints, and you know that, let me change to a different color here, and you know that there are these 2 points that have the same y value, okay? So the y coordinates of those 2 points are equal to one another. You know that if you have these 2 points where the y coordinates are equal to one another and your function is continuous everywhere and differentiable except for maybe at the endpoints, then you know that at some place in the middle of that interval, there has to be a spot where the first derivative equals 0. So really all that's saying is, you know, somewhere to get from here to here, maybe I'll go straight across, but maybe I'll have to go up and then down, or maybe down and then up, or maybe all over the place. But you know, at least somewhere in that interval, the first derivative would have to equal 0. So really that's just saying that you're going to reach a max or a min. You know, if f prime of c equals 0, you know you have a horizontal tangent line, right, at that spot, which means you're going to have a max or a min there, okay? So that's all it really says. It's no big thing. It's just it's used to prove a lot of the stuff we do later, okay? So in class we looked at, I'm going to go ahead and redo them here. We looked at number 11. So on that one, we have a function that's a polynomial just in factored form to make it easier on us. And we're considering the interval from 0 to 1. Okay, the part of this that is kind of new to you is actually determining whether Rolle's theorem applies. Then once you know it applies, you're just supposed to then find the point at which it reaches a max or a min in the interval. So basically, once you know you can use it, you just do the first derivative and figure out where the first derivative equals 0, okay? But before we do that, we have to consider this kind of thing. First off, f is differentiable because we just have a polynomial. Let me say continuous first. F is continuous. On 0, 1, and differentiable on the open interval. It's differentiable and continuous everywhere, really, since f is a polynomial. You don't have any trouble spots. Okay. All right, one more thing about being able to use Rolle's theorem. You have to check to make sure that f of 0 and f of 1 both equal the same thing. So you're going to plug those in. So this is what I should see if you get asked a question like this. Okay, so that would be 0 times something is 0. And if you plug in a 1, you're going to get a 0 as well from the other factor. Okay, so f of 0 does equal f of 1. Okay, so all of that is just telling you that Rolle's theorem applies. So I can use Rolle's, or I know from Rolle's theorem that there has to be a max or a min somewhere between 0 and 1. Okay, an x value that provides a max or a min somewhere between 0 and 1. So now your job is to find that. So what we did, so now we're trying to find it, okay? So now we're trying to look for it. So we're going to take the first derivative. And in this one, it's a product rule problem. So we'll do first times the derivative of the second, okay, plus the second times the derivative of the first. Remember, this is times over in here. And then you need to get that cleaned up, and you really are gonna have to set this equal to 0, so it's good to have things in factored form. So, remember when we were learning how to simplify stuff that sometimes we did this? So see how we can factor out an x minus 1? And what we'd have from from the first term, we'd have the x and the 2x left. And what we'd have from here is 1 of the x minus 1s, okay? So that means this f of x becomes f prime of x becomes x minus 1 times 3x minus 1. Now that helps us then, because what we've got to do is find out, well, where does this equal 0? We know it has to somewhere between 0 and 1. We're looking for where in that interval does that happen. We're looking for where in the open interval that happens. So it happens at 1, or it happens at 1/3 when you work that out. And we're looking for that spot in the open interval from 0 to 1. So that's why it's the 1/3 and not the 1. And then I can't remember whether they want you to find the y-coordinate of that point, of the point where that happens, or if they just want you to say, you know, at x equals 1/3, you know, the c value. I think they're going to just want that c value. If you needed the y-coordinate, you would go back up to the original function and plug in 1/3 to get that. But this is the spot in the interval from 0 to 1 where you would reach either a max or a min. And it's not really asking you what it turns out to be, okay? And actually, it's just where you're going to have a horizontal tangent line is all. All right, then we did another one in class. Let me get some more paper here. And we'll see if I can get that where I want it to be. See if I can insert a page break. Okay, so let's do a couple more from that section. Okay, right in front of that. There we go. Okay. The whole page here. All right, here we go. Okay, so we also looked at number 15 in class. So on 15, you had the function 1 minus x raised to the 2/3 power, and you wanted to look on the interval from -1 to 1. All right, so first off, that is really 1 minus the cube root of x squared. That's what f really is. And so underneath a cube root, you can really have anything. It doesn't have to be just positive numbers or 0. So I don't see any trouble spots there. Okay, so this should be a nice continuous function. All right, now we need to be sure it's also differentiable on the open interval from -1 to 1. And sometimes it's hard to tell. You can graph it and look for things like cusps or places where things are undefined. What I normally do is go ahead and take the derivative. I'm going to need it later anyway. Oops, when I do the derivative of 1 is gone. So this will be -2. Let's go ahead and look here when we do it. -2/3 x to the -1/3. So that's going to be -2 over 3 cube root of 3, okay? -2 over 3 cube root of x is what I meant to write, okay? All right, so that's my derivative. And by getting it in that form, by doing the derivative, now I can consider whether f is differentiable on that interval or not. And what I notice is that x can't be 0. So it's not differentiable at x equals 0. And see how that would have fallen in between -1 and 1? So right then, I know that Rolle's theorem doesn't apply, doesn't fit the conditions. So there's no guarantee you're going to have a max or a min between -1 and 1. Still might have one, but not because of Rolle's theorem. You don't know, okay? And see, you might have done f of 1, to check the endpoints, and you would have gotten 1 minus 1 squared, which is 0. I'll write that out, 1 minus 1 squared. 1 minus the cube root of 1 squared would be 1 minus 1. And if you checked the other endpoint, the cube root of -1 is -1, but when you square it, you still get 1. So you might have checked that and noticed that the endpoints are equal, that f of 1, the value of the function at the endpoints is the same. So that's another condition of Rolle's theorem. So that's met. Continuity, is met. The problem is that not differentiable on the interval. Oops, open interval from -1 to 1. So that's why it doesn't apply. So we can't use that to ensure the existence of a place where the first derivative equals 0. Okay. All right, let's do one more. Let's look at 13. We don't do enough of the trig ones, so I like to bring those up every now and then. All right, so here we had a trig function given to us, and the interval we're dealing with is pi over 8 and 3 pi over 8, which are not normal locations. Okay, so you're trying to see on this, remember, whether Rolle's theorem applies. So cosine is continuous everywhere and differentiable everywhere. Okay, so f is continuous on this and differentiable on the open interval from pi over 8 to 3 pi over 8. In fact, it's differentiable everywhere and continuous everywhere. Okay, now we have to check the endpoints and see that they're equal to one another. So we're going to do f of pi over 8. And when we put a pi over 8 in there, we get cosine of 4 pi over 8, which is pi over 2. Think about your unit circle. It's up here, which equals 0. Now, the endpoints don't always have to equal 0, but they need to equal the same thing for Rolle's theorem. When you plug in 3 pi over 8, then you'll get 3 pi over 2 that you need to do the cosine of. And 3 pi over 2 is down here, and that's also 0. So f of pi over 8 does equal f of 3 pi over 8. And again, it doesn't matter that they're equal to 0. They just need to be equal to each other. All right, so Rolle's theorem does apply, so we'll continue. So we'll do f prime of x. Okay, when we do, we got to use the chain rule. The derivative of cosine is sine, and remember it's negative. And then take the derivative of the inside, which is 4. And then it would be better to write that -4 sine 4x. All right, and we're looking, this is where it gets a little hard if you haven't done trig recently, and even if you had, this is a little bit tricky. So we're looking for where does that sine 4x equals 0. We know there's going to be a spot somewhere in the interval from pi over 8 to 3 pi over 8 where that happens, and we're looking for where that happens. So we'll divide by -4, work on getting the sign by itself. We're dividing. And then here is where it's a little trickier than you think. All right, so we know that 4x, since sine is going to equal 0 when you're here or here, 4x could equal 0 or any multiple of 2 pi. So 4x could equal 0 plus 2n pi, or 4x could equal, over here on this side, pi plus any multiple of 2 pi, which means x would equal 0 plus, I'm dividing by 4 now, 2n pi over 4, or x would equal pi over 4 plus 2n pi over 4. And that can be simplified. So x would equal 0 plus pi over 2 times n times pi over 2, so any multiple of pi over 2, or x would equal pi over 4 plus a multiple of pi over 2, okay? All right, so here's where what we would have done in trig is we would have started plugging in a 0 for n, a 1 for n, a 2 for n. Okay, when we plug in a 0 for n here, we would get, so let me just continue on this next sheet so you really see it. Okay, so we normally would then let n equal 0 and see what we get. So then if n is 0, we just get 0, okay? Well, remember the interval we're looking for is on pi over 8 to 3 pi over 8. This is the interval of interest here that we care about. 0 is not in that. So I'm going to go over to this other one and try it. Put in the 0, and we get pi over 4. Pi over 4 actually is in that interval because pi over 4 is the same as 2 pi over 8. So there's 1. Okay, and you just needed to find, it says, if so, find the point or points guaranteed to exist. So we found 1. We knew at least 1 exists, and then we have to maybe see if there's others. So let me let n equal 1 and see what would happen. Well, if I do 1 times pi over 2, I'm at pi over 2, and that's already bigger than 3 pi over 8. Pi over 2 is 4 pi over 8. So I don't have to go any further. I don't get anything from there because already I'm outside the interval. Okay, and then on this one, notice the same thing happens. When I put in a 1 up here, I'd get pi over 4 plus pi over 2, and then I'd be too big. So this is the only value. Oops, this is the only value right there. The simplified one is what you'd want to write. Okay, and if you needed the y-coordinate where that happened, you would go back not to your first derivative, but you'd go back up here to that, and you would plug in the pi over 4. Okay, but I think they just want the pi over 4. So we know that at c equals pi over 4, f prime of c would equal 0, and that's the spot within that interval of interest where that would happen. Okay, so be able to do that type of thing. That's what I want. All right, now the mean value theorem, we just kind of had to almost stop here, really just says this. It says if you have a continuous function, so it's nice and smooth, nice function that doesn't have any holes or gaps, and it's differentiable, which means it's nice and smooth. You don't have any like points that are called cusps or anything like that. So continuous is just, you don't have to, you don't have a hole or something that you have to jump over. Differentiable is it's nice and smooth, no pointy places. Then we know there's at least one point in here. So that's what this C is. It's a spot within this interval from A to B where if you look at the tangent line to the curve at that x value, it'll be the same as the average rate of change on the interval. So like if you have a function that's continuous and differentiable, and you select an interval like this from A to B, then if you look at the average rate of change from A to B, that's what this is. This is the average rate of change on AB. It's going to equal the instantaneous rate of change at some value, at some spot, some number, and that's what they're calling the C. Okay, so that's all it says. So your function might not be just a parabola that's opening down. If you've got the beginning and the end value of your interval and you know it's continuous and differentiable, crazy stuff can happen in here. But if it starts and ends there, you can find the average rate of change on the interval, and it would be equal to the value somewhere in here. You would have the value of the instantaneous rate of change being the same as that. Okay, that's what the mean value theorem says. So these are kind of like the other one where you first are going to make sure that the mean value theorem applies. And then you're going to go on after that and find the points that you know must exist because of it. And I thought we'd just do a couple of these, maybe like 21. So 21, the function we started with was 7 minus x squared. So that's just a quadratic function, just a parabola. Okay, and that's the interval. So we know f is both continuous and differentiable on that because it's continuous and differentiable everywhere. Everywhere. Since it is a polynomial. So it meets that first condition. And then see, you don't have the condition that f of a has to equal f of b. You just needed to check that was continuous and differentiable. And if so, we know if we were to do the average rate of change on this interval from -1 to 2, that we could find a point where the average rate of change equaled the instantaneous rate of change. All right, so look at the directions. They kind of, well, they don't talk you through it like I thought. Okay, so determine whether it exists, whether it can apply, and then find the points that you know exist. All right, so your process after that would be to do the average rate of change. It's not the first derivative. Average rate of change. That's slope between 2 points. So it'd be f of 2 minus f of -1 over 2 minus -1. That's average rate of change. So find that first. So you might want to go and do f of 2 kind of off right at the start. That would be 7 minus 4 or 3. And do f of -1, which would be 7 minus 1, which would equal 6. Then you can just come down here and substitute that in. So you have 3 minus 6 over 2 minus -1, which is really positive 3. So you're getting a -2 for your average rate of change. Okay. That's not true because that's a -3 over 3. That's a -1. Okay, that's it. Getting a -1 for your average rate of change. All right, so now pay attention to this part. So your job, what you now know is there's got to be a C value. You need to find this spot where the first derivative equals that. Okay, so what you're going to do now is you're going to do the first derivative of the function. So that would be -2x. Derivative of 7 is 0, and then bring the 2 down and be -2x to the first. Okay, so find the derivative in general, and then find out where does that equal -1. And so this one works out pretty good, and we just find out that's going to happen when x is 1/2. And see how that 1/2 is in the interval from -1 to 2? The mean value theorem says that that's got to be the case. That if your function's continuous and differentiable on some interval, that the average rate of change between any 2 points, you should be able to find a place where the first derivative equals that. And we just found it happens when x is 1/2. Okay. And we could plug 1/2 into the original function and find the y coordinate if they really want the ordered pair. All right, let's do another one, maybe one that involves a little more of the less familiar functions, like 26, in case you get something like that. And the interval we're doing is from 1 to e. So I know logarithms are a bit of a challenge sometimes. Okay. All right, so first, log function looks like this. Nice and smooth, and it's continuous everywhere on its domain. It's just its domain would be that 2x would have to be bigger than or equal to 0, which means x would have to be bigger than or equal to 0. So that's the domain here, that x is bigger than or equal to 0. Well, the interval of interest is further to the right than that, right? It's from 1 to e. So we're good. So f is continuous on that, and it's nice and smooth and differentiable on that. So we know that. That means we can apply the mean value theorem. And what the mean value theorem says is if we did the average rate of change of f from 1 to e, then we could then find just one spot where the instantaneous rate of change equaled that. So what you're going to do is work on your average rate of change. So you're going to do f of e minus f of 1, and then you're going to come down here and do x, the x values, which is e minus 1. And you're going to work that out, okay? So f of e would be ln of 2e, and then this is minus ln of 2 times 1, and then just e minus 1. Now, you're not real familiar with ln, so this can be a little tricky. Okay, one thing you might think of here, one thing that might help you simplify a little bit is remember those logarithmic rules that helped us when we were doing logarithmic differentiation. This would be natural log of 2 plus natural log of e, this right here. Okay. So that's what I'm going to do is a little bit of simplifying. So natural log of 2 plus natural log of e is what that ln of 2e could be changed into. Okay, and that's kind of why I'm using this as an example, because you don't have a lot of experience with these types. Let me get that moved back up. Okay. All right, and then the natural log of 2 minus the natural log of 2 is gone. And then ln e, these are inverse functions, okay? You got the same base. If you do ln e on your calculator, you'll get 1. All right, so that's the average rate of change. You don't want to do an approximation for that. You want to keep it. You want to keep that all worked out. Okay, now what this problem says, because it fits the mean value theorem, is that we ought to be able to find a spot, an x value somewhere in this interval here, so that the instantaneous rate of change equals 1 over e minus 1. So what we need to do is we need to do a first derivative on the original function, and it's a natural log. So with natural log, remember how you do 1 over 2x, but then you have to take the derivative of the inside, which is 2. So it turns out to just be 1 over x. And so what the mean value theorem says is we ought to be able to find a value for x here so that 1 over x equals what we got for the average rate of change. And if you don't just see how it's e minus 1, you could cross multiply to get there. So x would have to be e minus 1 for these two fractions to be equal. And that's what we were looking for. Okay, so that would be the answer. That's the value that we were assured should exist. Okay, all right, now I guess I should make sure you realize that that's actually between 1 and e. So you would do the 1 minus e on your, could do the 1 minus e on your calculator to get a decimal approximation. They're going to want e minus 1 on the computer. But you can do e to the first power if you don't have just an e button, and then subtract 1. And that turns out to be about 1.72. And so that falls, see, between, that falls right there, because e is like 2.72 about. So 1.72 would be in between these two. Okay. So there it is. All right, so I just want you to be able to do that right there. Okay, there's one application I thought I'd look at that deals with it. So you get one more bit of experience with it. But the real use of the mean value theorem is to justify why we do the integration the way we do. So it's really used later. Okay, so let's do a problem here that's actually a mean value problem. All right, so this one says we got this function here. Okay. All right, the population of a culture of cells. We got how it's growing over time, and t is bigger than or equal to 0, and t is weeks. P is the population number of cells that we have. All right, so it's asking me on part A to do average rate of change. So that's the slope concept. All right, and then it tells me the interval it wants me to use from 0 to 8. So first off, for the mean value theorem, or for me to be able to do this, I'd have to think about whether this function is continuous and differentiable, but it's a rational function. And see, notice how in the denominator, you got t plus 1, so t better not be -1. Okay, but it won't be, will it? Because they want me to be just bigger than or equal to 0, or the interval from 0 to 8. So it's not a continuous function. There's an issue at t equals -1, but it is continuous and differentiable when you restrict yourself to bigger than or equal to 0, or the interval from 0 to 8. So we can use the mean value theorem. So now we're ready to do it. So we're going to do P of 0 and find out what that is. Okay, we do that by going to the function and plugging in 0. And we get 0 over 1, which is 0. Then we do P of 8. So that's 100 times 8 over 8 plus 1. So that's 800 over 9. Okay. Then we plug into the formula. We think slope. So it should be P of 8 minus P of 0 over 8 minus 0. So P of 8 was the 800 over 9. P of 0 was 0, and 8 minus 0 is 8. So that right there is the average rate of change. We just have to simplify it. So that'd be 800 over 9 divided by 8. It's really times 1/8. So we're going to get an 800. Well, let me simplify before I multiply. We're going to get 800 over 72, or you might have noticed you could divide the 8 out of there, and you'd have 100 over 9. All right, so that's the answer to part A. That's the average rate of change of the population. Okay, now let's think about what that's saying. That's saying that the number of cells, the population or the number of cells, is increasing because it's positive at a rate of 100 over 9 cells per week on average. Doesn't mean it definitely does that. And so you can think about it like the population or the number of cells is growing, okay, increasing at a rate of 100/9 cells per week on average. So it doesn't mean from 0 to 8, it just grew like that. It could have done all sorts of other stuff in between, but that on average, you found that slope of that line to be 100/9. And then the mean value theorem says there's going to be some spot on the actual function. This is not it. It's not going to be a polynomial, but there's going to be some spot on the actual function where this average rate of change equals the instantaneous rate of change. And your job is to find that. So with part B, what you do is you take the derivative. So you find P of t. Okay, oops, P of t. I didn't start finding it, I just wrote P. All right, so we're going to do the derivative. We're going to do low times the derivative of the high minus the function on top, the high times the derivative of the low. Okay, all of that's divided by the low squared. All right, so let's see what happens. That's going to be 100t plus 100 minus 100t all over t plus 1 squared. So we get 100 on top okay. So we get that to be 100 on top and then t plus 1 squared on the bottom. So the mean value theorem is asking us to find where does this p prime of t, where does the first derivative equal what the average rate of change was? Okay. So this is what you got to solve. All right, now you might notice some things that make the solving process a little easier. If it had been just a regular proportion, you could have cross multiplied and that would still work. But you notice how you have 100 over something equals 100 over something. So you know that t plus 1, the denominators have to be equal. Otherwise, the fractions wouldn't be. You could also cross multiply. It would just wind up taking you a little more time. And then do you remember how to solve things like this? This is a quadratic. You got something squared equal to a number. So we can undo that by taking the square root of both sides. So we're going to do the square root. When you do, don't forget there's both a positive and a negative square root. Okay, so this is the square root of t plus 1 squared equals positive or negative square root of 9. So the square roots undo each other, and you get positive or negative 3 on the right, which means t could be either 3 or t plus 1 could equal negative 3. So subtract 1, and what you find out, okay, let me do that again. What you find out is that t equals 2, or at t equals negative 4, we're going to wind up having the first derivative wind up equaling the average rate of change. Okay. So now we go back and we think about it. On that problem, the interval of interest was from 0 to 8. From 0 to 8. We didn't have it make sense when t was a negative 4 anyway, right? So what we're going to do is say, okay, at t equals 2. Okay. P prime of t equals the average rate of change of p on the interval from 0 to 8. Okay. So you found a place where the slope of the tangent line would equal the slope of the line passing through the point at 0 and the point at 8. Okay. All right, well, that's about all I want you to know about those. Get rid of that. About mean value and Rolle's theorem. They're really primarily very important results that enable us to do everything we try to do, and a lot of what we try to do in calculus, like knowing there's a max or a min. Okay, it's just normally what we care about is just finding the max and the min, not showing that we know it exists, but just going on and finding it. So those problems are a little weird, I know. All right, now this result right here, I kept on here, I wanted to mention, because this is the result we're going to use starting next week. What it says is, if you have two functions, and when you found the formula for the derivative of those two functions, okay, if the derivatives are equal, then you know the original functions can only vary by a constant. All right, so like, say this is one of the functions. If I did the derivative of that, and it equaled the derivative of some other function, my other function would just be like that same thing, but maybe shifted c units this way. These two, f and g, would be such that f prime of g, the slope of f, would equal the slope of g, is basically what it's saying. Okay. Now, what that means is when we try to do antiderivatives, when we try to reverse the process, we need to keep that in mind. That, yeah, the derivative of g is something, but when we reverse that, there's going to be multiple functions that could have that derivative, but they would vary by a constant. All right, so that makes more sense, after you talk about antiderivatives. Okay. All right, I'm going to stop this video and do another one for the rest of this handout.